Okay, here we go. Okay, so this talk is about hello Exascale world with MPI and OpenMP. And let me just ask, have you guys used MPI before, right? So you know that you have a rank and you have a number of ranks, and this is the amount of parallelism you have in MPI if you're just doing MPI. And this has been around since the 1990s, right? And so all of a sudden we had many more cores, and so we added OpenMP to that. So you ended up having a number of threads in OpenMP times the number of ranks. And so that became the amount of parallelism you had. And if you remember when MPI just came out, you guys are very young, so you probably don't remember, all right? A lot of people said it was too complex to use, right? It required the domain programmer to decompose his application across the ranks. And then when OpenMP came along, same thing, too hard to use, okay? But to really effectively do the parallelism, the domain programmer had to decompose his applications based on the number of ranks and the number of threads, okay? So let's just talk about that. So at Exascale, though, there is going to be many more levels of parallelism, right? And to get to 10 billion ways, parallelism, you're going to need about 100,000 nodes, and on each node you're going to have about 100,000 way parallelism. So how are you going to get that? Are you going to have 100,000 threads? Not likely, and you're going to use some of the new principles of some of the new capabilities of OpenMP. So you have it's also very possible that the organization of your ranks in a cluster will be organized by a supernode. Okay, so you'll have a number of groups, and then you'll have a number of nodes within that group. So there's already one level of hierarchy that you'll have with MPI. Then within the node itself, you'll have a number of devices. Okay, that's actually also new in OpenMP, where you actually have the ability to support multiple offloading devices. Well, let's take a look inside a device. Okay, a device could be a NUMA node or a GPU. There are multiple cores inside there, or multiple streaming processors if it's a GPU. So you have this other thing here. In the case of OpenMP, we look at that as kind of like a team. It's not a direct correlation, but you have a team in OpenMP that would correlate to the streaming processor. Then, of course, the actual core itself gets you the total amount of parallelism. So at Exascale, this is sort of an order of, this is one potential way to get there. And these are only orders of magnitude, right? I'm not saying this is the way that anybody's going to build one, but to get to 10 billion ways, you need O of 10 to the 5th cluster nodes. That's about 100,000 nodes, and you need 10 to the 5th IP instructions per cycle on the node to get you to 10 billion ways, right? So the question is, what's that going to look like from the programmer's view in OpenMP? So the terminology here is going to be in terms of MPI. The new MPI 3 supports these new communication, I forget what they're called, communication primitives, and we can put things into groups, and we can actually have communication among just the ranks within a group, right? So you have groups, you got ranks, and then you got devices, you'll have teams and threads, right? So let's just back up a bit and talk about what we mentioned earlier, sort of look at the generations of decomposition as we went through time. So initially we had, we're getting cut off at the end there. Sorry about that. Can you see that MPI at the end? All right. All right. So, this was vintage 1980, 1990s, and I'm not sure what scale that was at. Then we had MPI plus OpenMP, so we had X of number of ranks, rank X of the number of ranks. We had thread Y of number of CPU cores. And here's where we're at today, I think, with petascale systems, right? Where you actually now add OpenMP acceleration on a lot of petascale type machines. And so here we introduce this notion of a thread within a team size. Now, OpenMP is using the word thread within a team, all right? Unfortunately, it's confusing with the thread on a CPU as well. In fact, when you go into an OMP target, the number of threads actually changes to the number of threads on the GPU. And so it's a different number if you did OMP get number of threads. So in a way, I don't like to reuse the term. So I want to use the term in my program item instead of thread so that I'm really clear. So when I say an item, I really mean a GPU thread, okay? So that's why I put the word item there. Now, the next thing, the pre-exascale systems that we're getting into today, like the Oak Ridge supercomputer, you're seeing many more devices on the node. You don't just see one accelerator. You'll see half a dozen devices. So in this case, it's the device D of the number of devices. So this is sort of 4 levels of parallelism. And I really believe that as we get towards real exascale, we're going to get to the 5th level, which is the grouping of the nodes, okay? Because the hierarchy across the cluster is really going to be important for and it kind of comes back to saying, the people will look at this and say, wow, just like they did in the past, no one's ever going to do this, right? It's too complex. Well, whether it's done implicitly by some other programming model or it's done explicitly by the programmer using OpenMP and MPI, you're going to have to deal with that level of parallelism going on. So it's better if you understand this and think from today, because the current OpenMP today supports this capability, and MPI. We can do this today. We can start thinking about how we would make our codes parallelizable, and we can even run this program on today's system. So, okay, here's an eye chart, right? So this is the source code for this hello world that I have. It's not all of it. It's just the top level file, because there's an initialization here what initializes MPI, it initializes OpenMP, it even initialized. I actually believe at Exascale we're all going to need a Power API. We're going to need to query Power, and I'll show you in a minute why we believe that you'll be running under a Power budget and how that will work. All right. So anyhow, I just want to calculate the total amount of parallelism here. It's the total number of groups times the number of group ranks, and this stuff, the initializer figured all this stuff out, and we put a nice little data structure called HEW that has all these values in it. It even has the values for what the current rank is and the current group number is. So then we get to the point, now this is a code that's running on a node, right? That has an MPI environment, and we already know what our rank is, we know what our group number is. Now we're going to, for each device, so we have for each of the devices that we have, we actually have to note the device number using the device clause in OpenMP. So that's what this is. And then you don't really need these are kind of defaulted, but I put them here to note that you can control the number of teams that a code region could use, and the number and the thread limit, which is the number of threads that it would use. But really, these are going to be something like the wavefront size on the particular GPU, and if it was an AMD, it would be 64. If it was NVIDIA, it would be 32, right? And then we OMP distribute. That says this next for loop is going to be distributed across the different teams, right? So this is saying for all teams in the device, and we say for all threads in a team, and then that's what this last for loop is. And then I don't want to have 10 billion lines of output, okay? So I have an if statement that says, of course, if your rank is this number and your device number is this and your team number is this, is 0 and your item is 0, then do the print hello world, right? Because the hello world at Exascale is going to say, I am group X of how many, and so this is what it will look like, all right? And so then I'm also calculating the amount of parallelism that you have on the CPU side of stuff. And then after you've printed, we do a power query, because we'd like to know how much power hello world took, right? And then we stop, and the stop is going to print a little epilogue, okay, that I've created. So here's the hello world, Exascale world. So you'll see group 0 of 144 groups. Now, I don't have a machine like this, okay? So I could run, it wouldn't be that interesting if I ran my hello world on the clusters that I have access to. So I actually have the ability to put to plug in to this code a simulation of a system, so that we can show what an Exascale system would look like, right? So this isn't, I did not run on a machine this large. This is running simulated values, but this code will run on existing machines or an existing subset of a machine, and you can get this kind of list. So you get a hello world, and it's kind of nice, because what do you do when you get a hello world? Now you have the initialization of all the subsystems. You can just worry about your code. So steal this template if you want. Just take this and say that's how it would work. So so take a look here. This total amount of CPU parallelism is about 7 million, okay, and 159 million in the amount of GPU parallelism. And anybody kind of, I was hoping that enough people here to guess what machine this is. It's a simulation of a machine that's not yet active, right? As we go through it, you might guess which one it is. So that was the user printed hello world, right? Now, I've also developed an epilogue so that at the end of a run, we just print out all of this more interesting information. The number of node groups, there was 144. The nodes per group of 24. So the total number of compute nodes in this cluster was 3,456. The number of ranks per group was 24. We did, this is actually unconventional. A lot of people today would say with some of the smaller nodes, 1 rank per node is enough. But what we're seeing with GPU codes that we would really want to have multiple ranks per node. But just for demonstration purposes, we did 1 rank per node, right? And then the total number of MPI ranks equals the number of nodes. And then the next level 3 of it is the number of devices per rank, or 6. It's a little bit more of a hint if anybody can guess which node, which machine this is, all right? But it is a specific machine that has not been brought up yet. So then the number of teams per device, 60, and the team size at 32. So that might tell you something as well, right? It probably is not an AMD GPU, right? And IPC per thread. So this is the vectorization capability per thread. How many instructions per cycle that you could run, and the product of these levels times the IPC is 159 million, right? And you can take this sort of into power statistics as well. So everyone sort of assumes that the frequency of the machines is always running at peak. And that's actually a good assumption for something as simple as Hello World, where there's no computation. So in Hello World, you can see that the max frequency was 1 gigahertz, and the average frequency was 1 gigahertz. So nothing ever was throttled, right? We ran at the peak frequency, nothing was throttled, and so, but there was also no computation going on. So the sampled power said we're at 2 megawatts of power, but the power budget on the machine, this is a constant, is 6 megawatts, all right? As a matter of fact, it's actually higher than 6 megawatts because that's the power budget just for the computational part, right? But for the whole machine itself, if you're in the whole machine, it's got a budget of about 10 megawatts. Right? It's another hint as to what machine this is. Okay, so you have 10 megawatts, and we're only used 30% of the total budget. This is 30% of the 6. So there wasn't a lot of computation. As a result, as you get closer to 100% of your budget, the system's going to actually throttle back and lower the frequency to stay within so that you stay within the budget power for your entire system, right? So there's software controlled frequency, and so you can see there's the device cluster petaflops is 159. The total cluster with the CPU is 180 petaflops, right? So this numbers here, the peak frequency for the machine is going to lower when we start throttling back to stay within the power constraint, right? So, what's kind of interesting is to look at the memory statistics here and the ratio of the computing memory bandwidth to compute. So if you start lowering the compute capacity, you get that ratio, which is really important, starts to improve a lot better. You really have much better ratio of memory bandwidth to computing. All right. How am I doing for time?
It's 3:31, so you've been at it for 16 minutes.
Okay. Good. All right. So so this is a simulated from a hypothetical cluster, and so the next thing shows us some memory statistics. This byte to flop ratio here. So if there was a situation where your code was doing real computation and it caused some kind of throttling, right? If your code was memory bound, it really wouldn't perform worse because it got lower frequency because it was waiting for memory, and this ratio would actually improve when the average frequency went down, right? Because the total rate of computation would go down. So that's kind of interesting aspect when we start dealing with power budgets at Exascale, and that's one of the reasons why I believe, in addition to MPI, in addition to OpenMP, we need an API to capture the power numbers, okay, so that we can show people that application users become aware that some potential throttling occurred to manage power, right? Because I believe that will be the case. These are very large machines with a fairly significant power budget. Okay. So any questions about that? So I'm just going to show this chart again because it kind of does a summary. This is the last chart to say that this is sort of a hardware view of an exascale system, or actually of honestly any system, if you just took away the orders of magnitude of any system today. And today with OpenMP, we have this capability to break things down to multiple devices, multiple teams, and of course the number of threads, which has always been there. Okay. So with that, is there any questions?
So can you tell us the OMP distribute, how it will distribute across
The question was, how does OMP distribute things across the node? Let's see, do I have the, let me bring the code back here. Yeah. All right. So when a target region starts for a GPU or for anything, when a target region starts, the environment assigns it a number of teams and a number of threads. If it doesn't have the concept of multiple streaming processors, the environment, the default environment will set it the number of teams to 1, but there will always be multiple teams. Okay. So in the case of a AMD or an NVIDIA GPU, there are multiple streaming processors. So we often set the number of teams to be number of streaming processors and the number of threads per team to be the wavefront size, so that we can have some asynchronicity, right? That's not always it's not always what you do. You can control the number of teams to come down to one team and have many threads in that team. You can actually say, if you've got a particular GPU that has 4,000 cores, you can say, 4,000 threads on one team. And there's some advantages to synchronization of items. Why, if you made it bigger, there's also some advantage to being able to synchronize between multiple teams. So the number of teams kind of correlates to the number of groups of threads of things that you would want. So from a hardware perspective, that's what's going on. From a software perspective, you actually can control this fairly easily. And it's usually, you don't control you can, but you don't reduce the number of threads. But who knows? I think a lot of this use model of acceleration with GPUs is relatively new. But there is this, you do have to decompose by teams. And when we looked at this numbers of items here, right? If you don't have a group today, right? I would recommend doing this today and setting the number of groups to 1, right? Just one group in a flat rank space. And the same is true with devices. Set the number of device. If you only have one device, but you still have the capability to react to changes in the numbers of devices, and you can think about decomposing your codes along those boundaries, because that's what's going to change. You will have more devices in the future. Those devices are going to be bigger devices with more streaming processors. I don't think that the number of threads per team will change very much. All right. Interestingly enough, it'll be 64 or 32 or 16, those sort of things. So, but yeah, this is just trying to give you some thought into how to decompose your problems to meet the kind of parallelism that we're going to see. And today's OpenMP will support this. So, any other questions?
So what was the machine that you were mentioning? Sorry, but
I'm just, again, this is, it's not a secret. It's only my guess from the literature that I've read as what the Summit supercomputer at Oak Ridge. It's an IBM machine with 6 NVIDIA cards on it. And I was told some of the power, you saw some of in the press how much power it was going to take. So some of the other things were contrived in terms of how much power it would have taken at idle, right? That was a guess, right? So just to make it look good in the simulator, I put those numbers. But it was really...
I was thinking it might be Aurora, but I wasn't sure.
Aurora, yeah. Yeah, it's kind of fun with the simulator that I have. It doesn't really simulate or run. It just allows me to demonstrate and print out numbers, print out an epilogue to give me some comparison of some guesses of things. So it's a lot of fun, and it is a fairly simple program. There's not a lot of code here, right? So.
regarding the power budget, won't today's providers already have the capability of handling power and reporting it to the user? Like, for instance, Tau, I think, has the capability of collecting power information
Yeah, that's a good question, and you do need some sort of power API to collect that, and power APIs are, are always, getting total energy is power over time, so it takes enough sampling to kind of get the power right. I only took one sample there of the power at that time, but a lot of people talk about energy minimization, right? And most people say, oh, the answer is just race to finish, right? Go as fast as you can to get to finish, and you'll save the total amount of energy. But you know what? The energy isn't what's budgeted. The instantaneous power into the machine, when you hit a threshold, that's what's budgeted. All right? So you have to kind of stay within a certain range, and if you get close to it, the hardware, for multiple reasons, including thermal conditions, hardware will throttle itself back. And change frequency. And you see this today on your laptop with GPUs and stuff in your laptop. You just keep looking at the proc CPU info, you'll see changes in frequency. That happens to deal with thermal effects, all right? This is frustrating, I think, for a lot of HPC programmers if they start seeing the frequencies change on them. But we are going to be in an era where we're over-provisioned with the computation for amount of power, the power budget that's available for that machine. So I think it is going to be an important part of the overall environment, so that we understand that when you see that average frequency drop below the peak frequency, that means there's been some amount of throttling that's happened, and I think that's really good to know, right? And at that, any other questions? Well, thank you, Richard.